Okay, we're going to work on section 4.2, which is exponential functions. Okay, so with exponential functions, we'll get started with a graph. So, of course, with exponential functions, it means that the variable is in the exponent position. So functions that are exponential look like f of x equals a to the x. Now, this a here is called your base, and x, of course, is your exponent. The base has to be greater than 0, so non-negative, and a cannot equal 1. Okay, so those are the restrictions on the exponential function. All right, so we're going to go ahead and get started by graphing an exponential function. So I get some graph paper here. Okay, and so let's take f of x equals 2 to the x, just for example. So we have f of x equals 2 to the x. If we want to graph that, we can make a table. So let's let x be negative 1. So then I'd have 2 to the negative 1, which is 1/2. Okay, remember how to make a negative exponent positive, you have to move to the denominator. That was from the review chapter. What if we let x be 0? A to the 0 is defined to be 1. Then we can have 2 to the first power, which is 2, 2 squared, which is 4, and so on. So as you graph this, you have negative 1/2, and 0, 1, and 1, 2, and then we have 2, 4. So you see, the graph that emerges is this one. You could plot more points if you needed to. You'll notice one thing about this function is that it is one-to-one, so it's going to have an inverse, which is going to be very important later on. You can note the domain is all real numbers. Now the range, there are no negative y's. It starts at 0, so it's 0, infinity. Notice I'm not including the 0, and that is because this curve, it gets really close to the x-axis but does not cross it. So it's increasing over its entire domain. So it's increasing over that domain, negative infinity to infinity. All right. Let's look at a value for a where it's a fractional value. Okay. So this case, let me get a different color here. So here, a is greater than 1. Of course, we know that a can't equal 1, but it can be greater than 1, as in this case. Now what we're going to do is look at what happens when a is between 0 and 1. And so here, we'll let f of x equal 1/2 to the x. Sometimes you'll see that with parentheses around it, sometimes not. It's implied that the entire 1/2 is the base, okay? So here, we'll make a little table, all right? And so we have here, just pick some values, so negative 1. So I have 1/2 to the negative 1, so that'll be 2. Then we have 0. Well, 1/2 to the 0 is just 1. And then we'll do 2. Well, let's just do 1, will be good. All right, and so that'll be 1/2. So as you graph, get yourself a graph going here. So what you'll have is negative 1, 2, which is right there, 0, 1, and then 1 comma a half. Okay, so we have this curve shaping up. Now you compare that to the other graph, okay, which was increasing. This one is decreasing over its entire domain. The domain is still negative infinity to infinity, but again, it is decreasing over that domain. The range is the same as before. It is still 0, comma infinity, because everything's above the x-axis, okay? We'll note one other commonality between these. You notice here that we have 0, comma 1 on this graph, and it's also on this graph. And that's true that 0, comma 1 is always on the graph of an exponential that has not been shifted around in some form or fashion, which we'll do some of those later. Here, notice that 1, comma 2 is on this graph. Well, the base is 2. So in general, that's like 1, comma a is on the graph. So far we have 0, comma 1, we have 1, comma a, and now here's this negative 1. We have negative 1, comma 1 all over a, right? And that's true for all exponentials that are haven't been translated. So you'll notice here you have 0, comma 1, 1, comma a, negative 1, comma 1 all over a. So to graph an exponential function, really all you need is 3 points, because you know based upon the behavior what it's going to do. If you get those 3 key points, then you're good to go. All right, and as we mentioned before, you can translate these. So if I had like 2 to the x plus 4, it would take that basic graph, right, that 2 to the x, and it would just shift it up 4 units. So instead of the x-axis being a horizontal asymptote, it would go up 4, right, and the graph gets shifted up there. So you kind of see there how shifts work. Likewise, you can shift it left, right, you can reflect it. So if I had, let's see, in black here, that was 2 to the x. Let's say I'm interested in 2 to the negative x. So, or conversely, well, let's start with 2 to the negative x, okay? So 2 to the negative x is like 2 to the negative 1 times x, and then 2 to the negative 1 is just 1/2. So we have 1/2 x. So basically, that's going to reflect our graph about the y-axis, which is, what we would think. So there's the graph of 2 to the negative x. Again, we replaced x with its opposite. So it's consistent with what we learned about before. And yeah, put the 2 to the x here, and then the negative out front, then that would reflect it about the x-axis, right? So here we have, see if I can get it here. So if this was our original graph, right there, then its reflection is going to be right here. So there's kind of the relationship among the graphs, so you can kind of practice with those. The other thing that's in this section is how to solve an exponential equation. So take, for example, 3 to the x plus 1 equals 9 to the x minus 3, okay? So in doing that, we use a rule. It says that if a to the m equals a to the n, that implies m equals n. Now that's a lot, all right? But basically it says as long as the bases match, as long as they're the same, we can set the exponents m and n equal to one another. Now you'll notice here that the bases don't match. We don't have a and a. but we can make them in that form by just converting 9 into 3 squared. So we have 3 to the x plus 1 equals 3 squared, and then that x minus 3. So now we have a to the m equals a to the n. So all you do is just set your exponents equal to one another. So this is going to equal that. So we have x plus 1 equals 2x minus 6, and then you can just solve. So you'll have x equals 7. Okay, we're solving an equation, so we want to put that in solution set notation. You can go back and plug in, make sure your answer works out, just like with regular equations. All right, let's see. Pick out another one. Let's do one with the transcendental number e. So e is Euler's number. Okay, so a Swiss mathematician, Leonhard Euler, came up with the number e. Again, it's transcendental, irrational. It's approximately 2.71, but it's just a constant. So e is roughly 2.7. So like if this were the graph of 2 to the x, right, then this would be the graph of 3 to the x. Then e to the x comes right there between them. Let's get a different color. So e to the x is going to be right there. So you don't treat it any different than you would a 2 to the x or a 3 to the x. It's just, a special number. So now you know how to graph e to the x, right? Solving equations with the e. Let's do number 78 in your book. So we have e to the 3 minus x equals e cubed to the negative x. Okay, so remember we need a for both bases. First of all, we have to get rid of those parentheses, right? So we have e to the 3 minus x equals e to the negative 3x. Since bases are like, we can set the exponents equal to one another. So here we have those. So we have 3 minus x equals negative 3x. Okay, and then we just solve. So we'll shift our x's to the left, constant to the right, and so we'll have 2x equals negative 3, so x is negative 3 halves.